Welcome to lecture 6. So today I'll briefly summarize what we have done before and introduce what we are going to do later, and this will complete in some sense the basic framework of the rest of the course. But before we start on semantics, let me just briefly go through the definition of the programming language PL0. Right, so we had this a program is defined as a block with some syntactic entity like a period. A block consists of a sequence of declarations, possibly empty, and a sequence of statements, also possibly empty. Declarations of various kinds which specify values or types or functionalities, as in the case of procedures. Statements is a particular syntactic or grammatical category which is specific to imperative languages, and PL0 is an imperative language because it's based on state changes. And we have this usual suite of statements, for example assignment, conditionals, loops, and we have so the conditionals and loops are usually dependent upon the truth of some condition, truth or falsity of some condition, and so we have various kinds of conditions. Most of them are relational, to do with arithmetic operators and their relations, and conditions in turn, and in general arithmetic in turn, mean the evaluation of expressions. So we have various kinds of expressions, the usual operators on expressions, and what we have done also is to take into account precedence of operators, so that you have a convenient way of writing unambiguous expressions without having to worry too much about parenthesizing them. So a large part of context-free grammars is really got to do with, let's say, parenthesizing things correctly, so that you can generate the right kinds of trees, right? So once the specificity of a context-free grammar also is such that you're interested in pragmatic issues like, is there a successful compilation procedure given the kind of grammar I've defined for the language? Is that compilation procedure efficient? If I change the compilation procedure, should I change the grammar in some way? If the compilation procedure does not work very well, is not able to parse for various reasons, how should I change the grammar? Okay, so the context-free grammars for specifying syntax is powerful enough so that you can consider alternate grammars which might simplify the problem of parsing your programs. Alternate but equivalent grammars. You could also it can also be coarse enough to specify just the broad outlines of the language. So as syntax, normally one would have to specify the grammar in sufficient detail so that firstly you're not restricted to a particular parsing strategy. In the case of PL0, in fact, that is one drawback. We have defined the grammar in such a way that it is actually a subclass of the set of all context-free languages. So the language itself has been defined so that it falls well within that subclass, So you can use various strategies for let's say parsing or compiling these programs in PL0. But on the other hand, the moment you include more powerful features, the moment your language becomes larger, your grammar also becomes very large, and it might be necessary to, for example, go outside this subclass in order to add more facilities. And by facilities you mean things that are convenient for the user, which don't hassle him unnecessarily, which means you might require to design more general grammars so that the specificity can be taken care of at the implementation time. Anyway, but the point is that you can specify a programming language syntax to a great level of detail with context-free grammars. And the important thing is, from the point of view of a user of the programming language, that level of detail is not needed. Most of the time, a user is only interested in knowing the abstract syntax of the language. I mean, how are the constructs to be? So an implementer's viewpoint of the language and a user's viewpoint differ in this very important aspect. You require a very coarse level grammar without ambiguity maybe for the purpose of the user, but you require a grammar which is fine enough so that the implementer has no trouble in designing a parser, for example, for this language. Okay, so there are various levels. So instead of restricting ourselves to a very highly formalized notation like a context-free grammar, at the level of the user, we might think of the user as being interested only in the abstract syntax trees which this for each program. So he would like to know essentially what would be the order of evaluation if he wrote a program in a certain way. For example, if he omitted some parentheses, if he omitted some semicolons or some sequencing operators, what would be the order of compilation? Does it make any semantic difference whether he introduces those parentheses or not? Right? So, and there's also another aspect. As I said, the context-free grammar formalism is not powerful enough to, for example, enforce certain context-sensitive features. Right? So the subject of semantics really deals with these problems. So let's for the moment not dwell too much on those context sensitive aspects of the language. Let's look further deeper down and see what exactly it is that we mean by a meaning. Okay, so there are various ways of looking at the notion of meaning. One is that you might just think of the meaning of a program as input-output behavior. Very often for interactive programs, sequences of inputs and outputs is what you're interested in. Or for many programs which can be divided up into neat procedures, you're more interested at the procedural level to determine what function that procedure represents. Right? So does a program, so can we say, supposing we do not have too much of I/O in the program, one viewpoint we can take is that every program is a function, or at least if it's an interactive program, we can divide up the program between its interactions and look at those segments which are free from any interaction with the outside world, from the user's interaction, let's say, and determine what function they represent. And if you want to determine what function they represent, then you also need to know what is the domain of the function, what is the range of the function, and by function I mean a mathematical function. So there are various schools of thought about, for example, how programs should be designed. Okay, so one very prominent viewpoint takes the view that essentially all programs are functions, are mathematical functions, which means they should have a clearly defined domain and a clearly defined range, and the program is just a notation to express a mathematical function. This viewpoint also subsumes the viewpoint that an algorithm is really also nothing more than a function. Okay, so if you take an algorithm as an abstract object, as abstract in the sense that it really has no concrete, its only concrete representation is a program that implements that algorithm, then really what you are looking for as a matter of correctness is to specify whether this program does not implement that algorithm. That's often not very important. What you are interested in is whether this program actually implements the function that that algorithm is meant to specify. Okay, so there is a mathematical function for which you do not have a computational for which you have an algorithm, which means that you have split up the computation of that mathematical function into various computational steps in some computational model in your mind. In our case, most of the time it's whatever is a computational model specified by von Neumann machines maybe. Okay, thus there is a computational model in mind whose primitives are used in specifying how a certain function is to be calculated. It's a method of calculation of some large function. By a large function, some function which has to be expressed in terms of the primitives of your computational model, so that you are actually able to evaluate for each argument of that function the value of the function at that point, right? So that is one thing. So there's a huge school of what is, I mean, a methodological thought which actually looks upon functionality as the primary motivation for writing programs. Algorithms are simply an intermediate step which are essential, because it's not the jump from a function to some very primitive and simple computational primitives is a very large jump, and so you require some coarse-grained intermediate steps so that you can start from the function, refine the function into some coarse-grained computational steps which you know intuitively are possible, refine each of those till you reach the primitives of the computational model, and that should be a program. Right? So but the point is that theoretically speaking, every program can be looked upon just as a mathematical function. Okay, you can, and very often that's also a convoluted way of looking at it, though it's theoretically sound. There is another property which is that very often you are really looking for what invariants or what other properties are either created by the program or what invariant properties are maintained by the program. So you can look upon programs as relating various data objects which the programs manipulate, but the way they manipulate them in such a so as to maintain certain invariant properties or to create fresh properties out of the data. That's also a way of looking at it. Okay, so you might look upon programs entirely in terms of sets of properties. So you can think of a program as completely being defined by a set of properties. An algorithm then, which is somewhat more abstract since it's an intermediate step between a function and a program, can be thought of as maintaining some subset of the final set of properties that you should achieve. So you are gradually adding to the properties that you require by refining your algorithm in various stages. So that also means you getting into a finer and finer level of detail when you write a program. So theoretically both these are tenable, because firstly every mathematical function is also a relation, and therefore any relation can be thought of as a property or as a collection of properties. Any relation or a collection of properties can also be thought of as defining some classes of functions. Okay, so the various schools of thought actually, even from the point of view of a user of a program, a user of a programming language, the question of what exactly does a program represent? It's some concrete notation for something in your mind, but is that something in your mind a function, a collection of properties, a collection of invariances? That is a matter of viewpoint. Okay, so the question of what constitute, but the main important thing is that it really does not matter, because all these viewpoints can be considered equivalent. You can always represent any sets of invariant properties as functions, any sets of function properties as relations or predicates, but largely it's a matter of so the attitude that most people would take is what seems more logical. I mean, if you were to look at a database program, to look upon a huge database program as a function from some domain to some range, I mean, it might be mathematically correct, but you know, what are you trying to do in a database system? You are trying to maintain certain consistency properties. That's in some sense a more not logical, but certainly that's one of the primary motivations in the maintenance of databases, going through transactions and maintaining consistency. Okay, so you maintain maybe some invariant properties, some consistency properties. You can also look upon programs and data in a different manner. For example, most of the normal programs can be thought of as data filtering through a program, okay, and getting altered on the transformation of data as a program executes. But in the case of a database, it somehow seems, a gut feeling would say that it's more like a program moving through a mass of data and making some transformations, going through some transformations, right? So there are various viewpoints you can take, and some viewpoints seem more tenable in certain problem specific areas, and some other viewpoints seem more tenable or more convenient in some other problem specific areas, right? So we will take the view at the moment that the meaning of a program, we will take an implementer's view. What is an implementer's view of a program? Well, an implementer's view of a program is that he should somehow specify state changes. For an implementer, the computational model is already present. A user need not even worry about the computational model, except to know that these things are there and he wants this. What he wants is completely different from, he doesn't, if you look at an ultimate customer of a software, he is not really interested in the state changes the program goes through, or in the state changes of a data item. What he is more interested maybe is just that it should implement this function, or it should maintain this relation, or it should maintain this property, or it should create a fresh property out of some mass of data. For example, a completely random sequence of items has to be sorted. It should create a property of, let's say, a sorted list out of the mass of data without changing the data. Right? So, from the point of view of an implementer, we might be interested, you might actually be interested in actually the step-by-step state changes. So the next question is, what constitutes program equivalence, or when can you consider two programs to be equivalent? One viewpoint is that you just, the step-by-step changes that take place should be the same. So given two programs, the state changes that take place should be the same. But that's not really right, because as I said, I mean, there are, for any particular mathematical function, there might be any number of different algorithms, and those various algorithms might use various different kinds of data. There might be different data representations. For example, if you take a simple problem like generating the first 100 primes, well, I can have different algorithms. One is the standard sieve of Eratosthenes, for example, which just you estimate, there are fairly accurate estimates of prime generation. Like for example, the n+1th prime is usually less than or equal to twice the nth prime. Okay, so in order to generate the first 100 primes of first n primes, you can take a large Boolean array and just knock out all the composites using the sieve of Eratosthenes algorithms. Or you can follow an algorithm in which you start with the prime 2 and systematically generate the next prime and the next prime till you reach your n primes. For each of these algorithms, there is almost an infinite number of programs which implement those algorithms. Okay, if you look at the problem as generating the first 100 primes and outputting them, then there could be a variety of algorithms of maybe different complexities, of different space requirements, and for each of those algorithms there is an infinite number of programs which implement those algorithms. So step-by-step state changes are not let's say a very interesting way of determining when two programs are equivalent. Two programs would still be equivalent if the functions they represent are the same. Note that it is possible to write the same function in several different ways, so the equivalence of functions is also important. Yeah. So we'll take the simplistic view that a program is just two programs are equivalent if they compute the same functions. In the case of interactive programs, you really cannot think of an interactive program as just one large function, but you can think of it as a sequence of input-output behaviors. Okay, between any two successive interactions there is a function, and we might think of program equivalence in the case of interactive programs as really a form of black box equivalence in which given two programs regarded as black boxes, for the same kinds of inputs you get the same kinds of outputs. Then you would consider the two black boxes to be the same. They need not be identical, because they could implement different algorithms, or they could both implement the same algorithm in several different ways. And so as far as program equivalence is concerned, we can take the view that the input output behavior should be the same, or the function that is computed, if it's not an interactive program, if it has a single source of input and a single output, you could think of it as the function that is computed by the program should be the same. Going a level lower, you have this notion of equivalence of algorithms. You have algorithms which are not equivalent in the sense that in the sense that they are either, one is either space inefficient compared to the other, or time inefficient compared to the other, and so on and so forth. But implicit in all this is that the two algorithms actually implement the same function. Yeah, you can compare two algorithms only if they both implement the same function or the same input output behavior. Otherwise, it's completely meaningless to say that one algorithm is better than the other. It's meaningless to say that a binary search algorithm is better than a quick sort algorithm. Because they really are for different functions. You can compare two sorting methods, you can compare two searching methods, which ultimately have to give the same function, but you cannot compare algorithms for different functions, right? So if you look at, when you look at this equality of functions computed, then what you are saying, so the equivalence of algorithms is just a comparison of efficiency, right? For equivalent for the same function, let's say, or for the same input output behavior. So when we are interested in program equivalence, our main view would be that two programs are equivalent if they represent the same function. Yeah, if they implement the same function. So this is what you might call the correctness problem. Okay, the correctness problem is that given a function, is it possible to show that a particular program actually implements that function? The program equivalence problem is, given two programs claiming to implement the same function, do they in fact implement the same function? Right? So it's only after you have gone through the correctness or the equivalence problem, it's only after you have gone through the correctness problem that you can really get into the efficiency problem. Which program is more efficient? After all, what applies to algorithms also applies to programs at a finer level of detail. Which program is more efficient than the other, in what way? Of course, they may be incomparable, because some program might use a large amount of space but do it in a very short time. Another program might use a large amount of time but use very little space, which could be a constraint in certain situations. Even then they may not be comparable, but at least the idea of even comparing them can only come up if you have already decided, if you have already proved that they both represent the same function. Yeah. So the equality of functions is, what we can do is, we can take the implementer's view of, what is the implementer's view of so we can take the implementer's view of step-by-step state changes, of being able to specify step-by-step state changes, and abstract out the function from that in order to decide whether the correctness problem has been solved for a particular program. The problem is that all of these have to be mutually interrelated, whether it's the user's viewpoint or the implementer's viewpoint. They all have to be equivalent in some way, right? So you have to be able to abstract out and prove properties about the program in order to show that the program is correct against a specification. Yeah, and in order to be able to compare two programs, you can compare them only after you have proved that they are equivalent. You can compare them for efficiency. So, right? So then, if you are talking about the meaning of a program, since it's a concrete object generated by syntactic grammatical rules, and there are an infinite number of programs generated by finitary processes of generation, the question of what constitutes the meaning of a program is something that also has to be is also something that has to be derived from some finitary object, which is the construction of the program from the syntax rules. Yeah, so there are an infinite number of programs in any programming language, and they represent various kinds of functions maybe, and the only way to be able to determine the meaning of a program is to be able to use the syntax as the basic framework from which the meaning of the program is to be derived, whether it is from the user's point of view or from the implementer's point of view. Right? So, as far as the meaning of a program is concerned from an implementer's point of view, or in fact the meaning of a programming language is concerned, it's closely linked to how you're going to derive meanings of individual programs. How can you derive a meaning for an individual program? Well, it will have to be derived from the construction of the program. Okay, so the meaning as far as an implementer of the language is concerned is what kinds of state changes are necessary in order to successfully implement each construct. After all, the only thing that is finitary in that programming language are the syntactic rules. Okay, and an implementer has to cater to an infinite number of possible programs that might be written by users of the language, which means that he has to be able to he has to be able to specify the runtime behavior of all those programs, and the only way to do that is to use the generational process of syntax. Okay, so using the syntax is absolutely essential. The syntax forms the basic framework for an implementer to specify the execution of an arbitrary syntactically valid program in the language. Right? So the syntax forms the basic framework, but of course, as I said, the syntax from the point of view of an implementer is a very detailed syntax. As I said, it avoids ambiguity, it takes precedence of operators into account. It sometimes, in order to suit the parsing algorithm, the grammar is changed in a certain way to make it convenient to implement, and so on and so forth, right? So, however, there is an abstract syntax for this language, which is a common platform of understanding between the implementer and the user of the programming language. And as far as the user is concerned, he should be able to derive the functional description of a program again from the syntax, but from the abstract syntax. So firstly, the abstract syntax and the concrete syntax should be equivalent, in the sense that if you look at the abstract syntax as a collection of trees, then the concrete syntax should generate exactly those trees. That is an implementer's problem. Okay, so there is an equivalence there, and the implementer should somehow faithfully, the abstract syntax is given a meaning which should be captured by the implementer. And if you can give abstract syntax meaning on a phrase by phrase basis, that means using the generational process of the abstract syntax, that the only thing that's finitary are these various productions, right? So you should be able to give the meaning of each construct, whether you are looking at it from the point of view of a user or from the point of view of an implementer. They should be able to give the meaning of each construct in the language in terms of the syntax that defines that construct. And you should be able to define how constructs are composed to form larger constructs. You should be able to define these larger constructors, the meaning of these larger constructors also in some form of isolation, and that should form the common document between the treaty between an implementer and a user. Otherwise one of them is going to yield unexpected behavior, right? So what it means is that now we have already seen that syntax is a fairly complex entity and can be quite intimidating. A normal user is not going to be able to come to grips with the syntax that is actually being used, the fine level of detail which the implementer requires. But the implementer, so the implementer should ensure that whatever syntax he uses faithfully captures the same set of trees that the user's view of the abstract syntax captures. And secondly, he should provide an execution behavior which matches exactly the functional behavior that the user has in mind for each construct. And both the user and the implementer should produce equivalent functional behaviors, right? So only then you can avoid misunderstandings, let's say, and that would also ensure that there is a meaning for the programming language completely independent of any other considerations. Okay, so the abstract syntax will form our basic framework for giving the meaning of a programming language. What we will do is we will use the abstract syntax. We know now how to convert abstract syntax into more concrete syntax and into implementation convenient grammars. But the point is that there has to be an understanding between implementer and user as to what is expected of each construct in the programming language, and both have to be able to derive the final behavior of the program from the behaviors of each individual construct in the language. Yeah. So when we look at meanings in a programming language, the various viewpoint, one is the designer's viewpoint, the language designer's viewpoint is that he is really providing a set of high level primitive functions. Okay, the idea of designing a high level language itself is that your original machine is too primitive to admit of convenient programming. And what does convenient programming mean? That I have some mathematical function and the machine operations are too small and too atomic for me to conveniently come down to that level and program every function at that level. So what as a language designer, what I do is I provide a set of high level primitives which may be conveniently used by some user to define whatever functions he is interested in. Yeah. So the designer's viewpoint is that he is providing a set of high level functions for a user. The implementer's view is that these high level functions somehow have to get translated into the low level functions of the machine, and so the step by step state changes actually define the implementation. And a user's viewpoint might just be that, look, I don't care about all these high level functions and so on and so forth, but just tell me how I can maintain these properties, even more high level properties. Yeah. So, and all these three viewpoints have to somehow gel together. So we won't go into great detail about these three viewpoints. So these three viewpoints form the subject of semantics of programming languages. One is called the denotational semantics. That is the viewpoint of, that's a purely functional viewpoint which just says that this construct denotes this function. There is an operational viewpoint which actually is the implementer's viewpoint. It's the high level it's a collection of high level translations that the implementer provides to implement the for the programming language. And the last is the axiomatic, which is what presumably one should use as a user, and all these three viewpoints should somehow be equivalent. And the equivalence of all these three viewpoints is called the full abstraction problem. The main problem in the 60s and 70s that people noticed was that most programming languages, and the problem still persists, do not really conform to the reference manual of the programming language, or that the reference manual for the programming language provided by the designer is not sufficiently detailed. Many implementers would read the reference manual and feel that it's not sufficiently detailed in its reference to in describing the functionality of certain features of the language, and very often the implementers had to take independent decisions. Okay, so many semantic issues actually moved into the area of pragmatics. The result was that a large number of programs had to be either patched up or rewritten when they were moved from one machine to another, and because there was this misunderstanding between implementer and designer. Yeah. Secondly, where in the early languages there was no reference manual even, what it meant was that there was complete chaos as far as implementations were concerned, and many users misinterpreted what if there is some level of detail which is not present in the reference manual, for which the implementer has to take a decision. The user's view could also be that some other decision was taken. So unless you try out particular implementations, you don't know what decision has been taken, right? So most of these, the problem of full abstraction actually still persists. Most languages are defined in some loose, ambiguous terms. Implementers are forced to take certain decisions because the language manual is silent on the issue. Most often it's silent on the issue, which is of importance to implementers, and very often it's ambiguous to a user what exactly the construct represents. It's ambiguous to he is not able to derive how a combination of constructs can, what behavior would a combination of those constructs yield, because he is not able to infer the meaning. There could be one of several possible meanings. that is actually implemented. Yeah, a classic case of this even now is the Ada programming language, okay, which is fairly recent in the sense that it went through a 10-year gestation period starting from about 76, when the US Department of Defense felt that the US Department of Defense had various installations all over the United States and of course abroad, and programs were not working, as simple as that. Programs could not be moved from one installation to another. There was a variety of languages, many of them the creation of committees within the Department of Defense itself, a variety of implementations for each of those languages, many of them created by subcommittees of the implementation committees, and there was complete chaos, right. So when they decided to actually that the effort of maintaining these programs, many of the Department of Defense programs are 40 years old, and they can't easily rewrite them because the price of competent programmers is very high. And so what they decided was that they are going to embark on a unified language for all matters concerning defense programming except for the business programming. So they assumed that COBOL, which is also created by a committee, is good enough for business kind of environment, and for all scientific, embedded systems, real-time systems, control systems, they would have one unified programming language. So they went through this process of design over 10 years by actually deciding that perhaps they were incompetent themselves, so they should subcontract it to somebody else. And if you see the Ada programming language reference manual, which came out sometime in the 80s, it's extremely ambiguous, it's extremely voluminous for one thing, it's extremely ambiguous on various issues, and there were no implementations at that time, so you couldn't even try out, you couldn't even experiment with the thing, but you had to take certain implementation decisions. It was silent on a variety of issues, far too detailed on a variety of other issues, and they specified that there should be no subsets supported. So the resulting document is a huge document which is very, very difficult to understand. Yeah, the syntax is clear but the semantics is not, right. So we'll look at the problem of so we will not go through all these different things. At various stages in your programming life you will come across these things. For example, many of you may have used a functional language for which a denotational semantics is very easy to specify. For example, scheme. Many of you may have used some axiomatic method, at least even if you are not used, you were probably told to use them, so we will be primarily concerned with operational semantics, and that is the implementer's viewpoint from a given broad understanding, let's say an informal understanding of what function the construct represents. So for each construct we will give an operational meaning. However, we do not want to give any kind of meaning which is machine specific or architecture specific, okay, because if you have to give an operational meaning, again there are several grains of there are several levels of granularity at which you can give an operational meaning, and we would not like to be restricted by either a machine or an architecture. We will just try to give meanings in machine and architecture independent forms as far as possible. Yeah, it used to be a common practice some time ago to define for a language reference manual to define an abstract machine into which they translated each construct in an effort to give a meaning to each construct of the programming language. However, more and more it's being realized that that does not suit a lot of people. It does not suit users, it does not suit designers, it's sometimes too specific. So a nice method of operational specification has now emerged in the last 10 years, which is machine independent, architecture independent, and is still able to give to a user it gives a step by step state changes, but it's also able to perform abstractions so that you get maybe purely functional descriptions. You can mix and match your level of detail in this operational semantics. Yeah, you can become extremely machine specific, or you can become extremely you can become almost denotational in whatever you specify. Right. So we'll use this as a general method for specifying semantics or the meanings of constructs, which for our purposes basically means the runtime behavior of programs. Okay. Any kind of semantics of a large program has to be derivable from the semantics of the smaller constructs which make it up. So which means an essential portion of the semantics hinges on being able to use the abstract syntax trees or the grammar rules in order to be able to specify the semantics. Yeah. So we will since we understand now how we can go from an abstract grammar to more concrete grammars in some fairly simple fashion, and we would not like to be restricted by, we would not like to be hindered by parsing strategies or scanning strategies unless it's absolutely essential. We will just consider abstract syntax trees and specify meanings of abstract syntax trees. So the compromises we make are that the abstract syntax trees anyway form the common level of syntactical understanding between a designer and a user and an implementer. And our operational semantics, well, while it's somewhat closer to the user, to the implementer's view, can be abstracted out to provide a user's view, and it's sufficiently abstract not to get into the details of the machine architecture or the machine language. Okay, so it's a reasonable compromise in a general kind of course like this to give an operational meaning which is architecture independent, which is machine independent, and which depends only upon the abstract syntax trees, because the abstract syntax trees provide a method of induction. Induction on trees is a powerful method which you can use to derive meanings of complex constructs from simpler constructs. Yeah. So we'll define for PL0 initially without declarations as semantics, and that should familiarize you with the general method of operational specification. Yeah. So the language of programming languages, the subject of programming languages is becoming more and more formal, and I think we should keep up with it. Right. Okay then, thank you.